Okay, so let's come on to chapter 3. And by the way, from now until the next 4 or 5 weeks, 7 weeks maybe, please always have your calculator ready. Okay, so if you had your calculator today also, please have it handy because we're going to start doing calculations from now until 4 or 5, 3, 4 chapters. Okay, all right. Okay, at least one advantage the PowerPoint people have is they don't have to erase the board, right? Just do click, 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 and go ahead. Okay, let's talk about chemical formulas and such. Chapter 3 is all about calculations and formulas and masses, okay, of compounds. You will be dealing with elements, you'll be dealing with atoms, you'll be dealing with compounds, molecules, everything, okay, in here. So all of these concepts should be clear in your mind. Let's talk a little bit about the structure, okay, that we have for compounds. There are different ways that we classify compounds, okay, in different formulas. And so let me give those first to you. The first is what we call the empirical formula. And an empirical formula is the smallest ratio of atoms in a compound. Write me the formula for manganese 4 oxide. As soon as you see 4, you know that it is a transition metal, okay? All right, good. Mn? What's the charge on Mn? 4 plus, and then you have oxygen, which is 2 minus, okay? And if you did the crisscross method, which is what you should do, okay, all the time, it just works fantastic, is this. And so you have Mn, and then 2, and then O would be 4, okay? Technically, this is what you would have. However, this is not the actual formula because this is 2 and 4, so which means you will divide it by the smallest number, which is 2. So you can divide this by 2, and then you can get MnO2. That's the correct formula. So you should always bring it down to the lowest formula. This is empirical formula that we're talking about. It's the lowest ratio possible. What has empirical formulas? Almost all ionic compounds have empirical formulas. Okay, even a lot of covalent compounds that you have done so far, almost all of them will have empirical formulas, which means that when you form the compound, you bring it down to the lowest ratio, okay? All right, then you get to the next one, which is called the molecular formula. And this is the actual ratio of elements in a compound. So even if we take this example, this is the empirical formula, MnO2, okay, for manganese 4 oxide. This may be the empirical formula, but it's highly likely, it's possible, okay, that when you actually go to find manganese 4 oxide, it exists like this, okay, whereas in Mn2O4, it does not usually, okay, but it's possible that it does. This usually does not happen in ionic compounds. For ionic compounds, the empirical formula and the molecular formula is the same thing, okay, for ionic compounds. Covalent compounds, on the other hand, they're a little bit more notorious. So let me give you an example of molecular formula and empirical formula. So for example, you can have CH2O. This is an empirical formula. I can take this empirical formula, I can multiply that by 6, and I can get C6H12O6, and this is glucose. Okay, yeah. Did somebody say fructose? No, okay. Because it is fructose too. Okay, it is also fructose. Fructose has the same formula as glucose. Okay, it has the same molecular formula. And that's the problem, okay, with some of these things, is that you don't know what the formula belongs to, because the molecular formula can belong to so many compounds then. Okay, all right. But how you get that molecular formula is by taking the empirical formula and multiplying it by an integer. Okay, over here, and that's how you get it. That integer may be 2, could be 3, 4, 5, 10, whatever it is. Okay, so question, anyone?
When you're multiplying it out, does it matter what number it is?
Well, it does, yes, it does matter. So, but then the question is, how do you know? How do you know? Okay, I knew that I was multiplying it by 6, but can you multiply this by 4? And technically, yes, in this case you can, because this is what we call carbohydrates. Okay, and carbohydrates have a big family. Okay, this is one of the biggest families out there. Okay, carbohydrates. So you can multiply it by 3, 4, 5, 6, 7, and still get the right molecular formula. Okay, but a lot of times it may not work that way. So in those cases, you need to know how to get this number, and this is an experimental thing that you have to do. Okay, so which is where we're going, okay, in this chapter. So you have to do experiments to figure out the empirical formula, and then you have to do experiments to figure out what integer to multiply it with, okay, in order to get the actual molecular formula. All right, so that's the molecular formula. Then the third thing, maybe I should number these things, 1, 2, and then 3, is what we call the structural formula. And this is the 3D representation of a molecule. And the 3D representation of a molecule comes a little bit later. Once you know what the molecular formula is, then you can propose a structure for it, okay, which we are going to do in chapter 10, okay, when we learn about molecules, and then we'll learn about how they look in 3D. All right, so we're going to go there eventually also. All right, so this is called the structure formula. In this chapter, we will stay with empirical formula and molecular formula. Good so far? Questions? No. Okay. All right. Feel free to ask questions. You know, you're supposed to ask questions. Okay. Now let's talk about the mole. Formula, mass in the mole. This is something that once you learn, you will never, ever let go, okay? Because you have to just know it for everything, all right? So please learn it. I was going to say goodly, okay, not a good language there, okay? Learn it well, okay? Learn it well. And if you don't understand this, this is something that you definitely should get help with if you don't get it, okay? Because you will use the mole concept now and later, and organic, biochemistry, everywhere, okay? So it's really important you get this. Okay, first of all, let's talk about mass, okay? And you know the periodic table already, and you know that the periodic table is based on atomic number. And then the other number that's given there is the mass number, right? And the mass number that you're getting is an average of isotopes, okay? When you were trying to calculate the number of neutrons and protons, remember that one worksheet that I gave you where you had the table in there and you had to write out the number of neutrons and all that? Please, when you do those calculations, do not write the number of neutrons in decimal points, because you know that doesn't happen, okay? When you have particles, they always occur in whole numbers, all right? And so when you're doing that, go ahead and round it off, okay, to the nearest number that you think possible, all right? And that's it. That's how you do it, and then there's, you know, no worries about whether you're right or wrong, because you will be right, okay? So round it off and work like that. That's how you calculate the number of particles in there, okay, number of neutrons. But when you're calculating the mass of anything, for masses, you will use exactly the same mass that's given to you, okay? So now if you look at this mass that's given on this periodic table and the mass that I gave you on the other periodic table, and you also have this periodic table, and you also have one at the back of your lab book, right? So you have all of these periodic tables. If you start comparing all of these periodic tables, you will see that the masses are slightly different, okay, in all of them. So which one do you use? Well, you use the one that's available to you, okay? That's all you can do. all right? So go with the one that's available to you. In an exam, everybody's gonna have the same answer because I will give this yellow one, okay, to everybody. So that's the one you're supposed to use, don't use this one, okay? And of course, then there are some numbers in here which go up to 5 decimal places and some go up to 3 decimal places, okay? The general rule for me that I follow, okay, for myself, is when I calculate the masses for anything, I use up to 3 decimal places, okay? I don't go farther than that. By the time you get to the 4th or the 5th decimal place, it doesn't make a dent in your calculations, okay? It's not gonna affect anything. So the best thing to do is round it off to 3 decimal places. So you can follow the same rule also, okay? From now on, when we're calculating the mass, then use 3 decimal places. And you will see that once you start doing that for all the periodic tables, it will come out to be the same. But in some cases, you are given only 2 decimal places, okay? So here for strontium, you're given 87.62. So then what do? Well, then you just use that, okay? Then you don't have any choice, okay, in these cases. Remember again, when you do calculations in the lab, in what we're going to do now, your data is the most important one. Remember that. Okay, I've always stressed that for you when you were doing conversions also, that whatever number of significant figures you have in your data that's given to you in the problem, that's more important. Everything else is a conversion factor. Okay, so even if you have 5 significant figures over here, it doesn't matter. Okay, so your data is what's going to matter. If it's only 3 significant figures there, your final answer should be in 3 significant figures. All right, keep that in mind as you're working. Otherwise, you'll go cuckoo, okay, trying to figure out what to do here. All right, so keep that in mind as you go. All right, so now when we look at the periodic table and we start looking at the masses of things. So for example, lithium is 6.941. And right now, the units we are using is, anyone remember?
AMU.
Very good. Okay, give you a clue there. AMU, atomic mass unit. Okay, that's what you're using. We're going to change that, okay, in a little bit. But right now, you're just using atomic mass unit, okay, for this. So 6.941, that's the atomic mass unit, and that's the mass, okay, that we will say for lithium. And you know that the mass is equal to the number of protons and neutrons, okay, coming from the atom. Okay, so that is for lithium. You can pick any atom from there, okay. So for example, scandium is 44.95591 AMU, okay. Iron is 55.847 AMU, okay, so on and so forth. So you can pick up any of those, okay, in there. This is what we call atomic mass because it's coming from an atom. So it's an atomic mass. Now we're going to get into what's called the molecular mass, okay, or molecular mass or formula mass. And in case of molecular and formula mass, you're working with a molecule or a formula. And you remember, and I said before, that covalent compounds are considered to be molecules, whereas the ionic compounds are considered as formula units. Okay, and that's why you will see that I just use molecules for everything. Okay, so that there is no confusion and I don't have to worry. Or I just go back and I use compound. That's it for myself. So I don't have to think about, you know, what it is, because essentially it's a combination of atoms. Okay, whether it's covalent or ionic, it doesn't matter. It's still a compound. Okay, so I just use compound just for the ease of everything. So now, for a molecular formula or a formula mass, things are a little bit different, because if I have chlorine, okay, and I in my periodic table, somebody took it, but here. For chlorine, the mass is 35.453 AMU, but for Cl2, the mass is not going to be this, because I have 2 atoms of chlorine. So if I have 2 atoms of chlorine, then it will be 35.453 times 2 AMU. And that's why you need your calculators handy and ready, so you can do all of these things fast. Okay, you're not multiplying there. And please don't use your cell phones. Okay, you will not have that in the exam, so get to know your calculator well when you're doing all of these things, and you will need to help me out as well. 71? No, 79. 79?
No, 70.906.
906 AMU. Okay. Sorry, hard of hearing. Okay.
I was mumbling.
So Cl2 would be this much, okay? One of your first tasks for this chapter is to even just calculate these masses, okay? That's it. Which means that you really have to have good nomenclature. If your nomenclature is not good, then your formula is not going to be correct, okay? So if you don't know the formula for, let's say, water, then you don't know that you have 2 hydrogens in there and 1 oxygen, okay? I should probably give you a list of some common molecules, right? Because water, we called it dihydrogen monoxide, right? Yeah. So I should give you some common names, okay, that you will encounter. So water, for example, is H2O. There's another one, methane, which is CH4. Ammonia, you have not required yet, you haven't encountered yet. Ammonia is NH3. These names have nothing to do with what elements we're talking about. Okay, it's very different. Nobody calls ammonia nitrogen tetrahydride. Okay, nobody will call it that. We just call it ammonia.
And H4 is ammonia.
That is ammonium.
But they're like close to the same.
They're very close. Yes, that is true. Okay, but again, even that doesn't tell you that you have nitrogen in there. Okay, yeah, that's what I meant. So, but anyhow, these are some of the common names, okay, that you will encounter for molecules. So H2O. This is what I do when I'm calculating my molecular formulas, okay, for masses, is I will break it down, okay, into what elements I have. So I have H and I have oxygen. Oxygen is the one thing that you have to be really, really careful about because oxygen also looks like 0. Okay, so you have to be really careful, okay, with that. So what I do then is I write 2 hydrogen and 1 oxygen, and this is where it gets really weird because is this 10 or is it 10? All right, so please be very careful, okay, when you're doing this. So this is 2 hydrogen. If you want, you can write a little multiplication sign there so you know that you have 1 numbers and then you have the letters, okay, going on there. So once you have this, then 2 times you find the mass of hydrogen from there, which is 1.00794, and then 1 times, which is 15.9994. And initially, you may need to do this little slowly so that you don't mess up anything, 15.994, although I will tell you that I still use this method. Okay, so I don't lose any atoms this way. Okay, if I have a bigger formula, this is still what I would do. Okay, and so 2.10588. What is it?
2.0158.
Okay, all right. And then you add these 2 up. Okay, yeah, because after the third number, it doesn't really matter. Third decimal place. So then you add these up, okay, together, and so the mass will come out to be something like 17 point something.
18.
18.
0.009.
AMU. Please don't forget the units, okay, for it. So it's AMU.
It's 980. So would you round it up to 18.01?
Sure. We'll make you happy today. Okay. We'll take the same one that we had before. Calcium sulfate. If you're calculating the mass of this, then what I would do, I would separate this out. Find the mass of each of them, 1 times calcium, 1 times sulfur, 4 times, and of course I have that written out right there. Okay, and then you do the addition of everything there. Keep it systematic, and calcium is 40.078 and sulfur is 32.066. And 4 times 15.999 and then 4. 63.976 plus 32.066 plus 40.078, 136.12 AMU. where you have like calcium nitrate. If you have something like this, make sure that you multiply everything that you have inside in the brackets by 2 or whatever number, okay, that there is supposed to be. So please don't forget to do that. So here this will be calcium, 2 nitrogen, and then 6 oxygens, okay? What I do is I keep my numbers column over here and my alphabet column there so that I don't get messed up, okay, with that. All right, so now you know how to calculate the formula mass, and this is the first thing that you do, okay, is calculating formula masses for anything. Okay, so now let's talk about mass in general. And we will take calcium sulfate because we've done this one. Hydrogen is about 2 mu. Chlorine is about what is it, 71, let's just round it off. And calcium sulfate is about 136 AMU. I want to take you a little bit deeper into the structure, okay, or what this really all means for us, because right now this is AMU. You can't go into the lab and you say that, oh, I want 3 AMU. Oh, what is 3 AMU? Okay, that is not a measurement for us. The measurement is in grams, it's in milliliters. Okay, that's where our measurement is. So that's where we need to go with this. We can't have AMU in there. Okay, all right. So I'll give you a conceptual problem, okay, to think about. If I have 1 gram of each of these, if I have 1 gram of each of these, which one has the largest number of atoms? You want me to change the calcium sulfate if it's bothering you? Is it bothering you? No? It's all right? Okay. It's bothering me a little bit because it already has so many atoms in there. Okay, so hold on. Let's take something else. Let's take iodine because it's simple to calculate. Let's take iodine. What is it? 126 points, 127 times 2. 254 AMU, approximately. So you have 1 gram of these 3 elements. Which one has the largest number of atoms in it? Iodine? Okay, you can call it iodine too. I know, it's just me. Okay. Are they all going to be the same? Think carefully, okay? Think carefully, and that's why I wrote the AMU as well, okay, the atomic mass unit, because the atomic mass unit is the number of protons and neutrons, okay, that you have in there. So that's the mass of the atom, okay? So how many atoms do you need to get 1 gram of iodine? How many atoms do you need to get 1 gram of chlorine? How many atoms do you need to get 1 gram of hydrogen? Think of it that way. So how many atoms do you need for hydrogen? A lot, tons of it, or very few will make up 1 gram? A lot compared to iodine?
You're going to need more hydrogen than iodine.
Yes?
Because it has a lower AMU.
Because it has a lower AMU. That's the concept I would like you to understand. Okay? Because when you get to the masses of atoms, this is the conceptual thing. Okay? And if you understand that concept, then things become a little bit easier. Okay? Which means that I'm going towards the concept of an atom is lighter and something is heavier. All right, here. So hydrogen is a lighter atom because it is only 2 AMU. Whereas iodine is much heavier, which means it will take very few iodine atoms to get you to 1 gram. It will take a lot of hydrogen atoms to get you to 1 gram. Does it make sense? Are we good, Max, there? Okay, all right. So it's the other way around. Okay, so hydrogen is going to have large number of atoms. This is the largest one. Okay, in there. And iodine is going to have the least number. That will hopefully give you the concept of heavy atom and a lighter atom. So hydrogen is a very, very light atom, okay? All right, which means that if you're going in the lab and you're trying to weigh out 1 gram of hydrogen, you will have a lot of atoms in there, okay? All right. From chapter 2, you will also remember the law of conservation of mass, okay? Dalton's atomic theory. And Dalton's atomic theory stated, one of them, not all of them, one of them stated that in a chemical reaction, you have a rearrangement of atoms, nothing gets lost, okay? And then nothing is created, you only rearrange atoms, okay? Which means that we are really talking about atoms here. We're not talking about grams, we're talking about atoms, okay? And just now we decided that hydrogen has way more number of atoms than iodine does. Do you see what I mean? Which means that if you need the same number of atoms, we're talking about different amount of mass, correct? All right, so now let's take it the other way, which means that if I had 100 atoms of hydrogen and I had 100 atoms of iodine, which one is heavier? Everybody together. Iodine, okay, because the hydrogen atoms are way lighter, okay? All right. But now at least I have equal number of atoms. You see that? Okay. According to the law of conservation of mass, it says mass, okay? But essentially when you get down to it, it's all about the atoms, okay? And so in a chemical reaction, when atoms get rearranged, you want to make sure that you have the right number of atoms, not the right amount of mass, okay? All right, that's the key thing when we start getting into what's called the mole concept then. Okay, so then how do you know? How do you know atoms? Because how can you count the number of atoms? Remember, atom is a very small thing, okay? Extremely small, so you can't even see it, all right? There is just no way. The mass of the proton was like 10 to the negative 27 kilograms, right? So it's a very tiny particle. So we can't see atoms, so which means we have to have some other ways, okay, to make the connection between the number of atoms and the mass of the atom, okay, and that was done by Avogadro. Black pen. And Avogadro was an Italian chemist who came up with this number, and he said 6.023 times 10 to the power of 23 atoms is equal to 1 mole of atoms and this doesn't help us still because we're still talking about atoms, and atoms doesn't do anything for us. We need to get to grams, okay? So then that takes us to equal to atomic mass. That's the relationship between these three things here. I'm going to write it in the reverse order, okay? Because it's easier to understand from mass, because that's not a concept that we understand. We understand masses. We don't understand atoms that well sometimes, okay? But the mass, sure, I know what a gram is, okay? So I'm going to pick any element from there, and let's take carbon. Carbon is 12.01. If I go into the lab and I weigh out 12.01 grams of carbon, how many atoms of carbon will I have? 1. That's what I will have. Okay? So the atomic mass that's on the periodic table is for that many number of atoms. And that many number of atoms is equal to 1 mole of atoms. The short form of mole, M-O-L-E, is M-O-L. We just take off the E. Such a big difference. Okay? You can take literally anything from the periodic table, okay, and that will mean the same thing. So for example, If I were to take something even as heavy as, let's see, gold, 196.9 or 197, 197 grams of gold is going to be 1 mole, and this is going to be equal to 6.023 times 10 to the power of 23 atoms. Okay, that's a lot of atoms. Yes, but then gold is also very heavy. Okay, so which means that if you have the same number of atoms of gold and carbon, they're going to weigh different, obviously, because carbon weighs a lot less. Okay, there. Are we getting the concept now? Okay, we're good? All right. Okay, and that is how we relate what we have on the periodic table to the mass, to the number of atoms, because ultimately for us, everything comes down to atoms. Okay, how many number of atoms do we have? And in this chapter, we have to do a lot of reactions also. Okay, all right. Let me divide this by 2. So let's say you have about 6 grams of carbon. How many atoms will I have now? I will take this and also divide it by 2. See, there's a ratio there then, okay, that you can use, which means that that is my conversion factor also, okay? All right. I'm going to change the units for you now, okay, for the periodic table, because right now we're using AMU as our units, but now I'm going to change it because the periodic table masses now that we have is actually gram per mole. That's the unit you're going to use now, because that's the number of grams you have in every mole of atom, or excuse me, every mole of substance. And that mole of substance is equal to this many number of atoms. Okay? This number over here, Avogadro's number, it's a very important number because it tells you how many atoms you're dealing with. Sadly, you don't use it that much. You use it in calculations sometimes, but you don't use it all the time. Okay, the 2 main things that you'll be using from here is the mole and the grams. Okay, everything relates to moles for us. Okay, everything comes down to moles. So the mole concept really is a relationship between the number of atoms and the grams, okay, of any substance. That's how we relate it. So mole becomes like a general measurement. Okay, so for example, do you know what a dozen is? Yes, 12. For us, a mole is this much. That's it. Okay, so just like dozen is just a unit that tells you how much something is in there. Okay, the quantity of something. A mole tells us the quantity of atoms in there. Okay, and that's a very specific number. Just like for dozen, it's 12. For a mole, it's this big number. Okay, by the way, you will never forget this number. Even in your deathbed, you'll be saying, I still remember this number, because you will never forget it. It's that unique. Okay, how did he get this number? How did he get this number? Yes, Jake.
Well, I learned it with amount of atoms in a gram of hydrogen.
Yes, but how do you come up with that number? Mathematically, how do you come up with that number? Because 10 to the power 23, can you write 23 zeros on a 1? It will take up your whole book. Right? So conceptually, when you think about it, 23 zeros is really a lot of zeros. Okay, so how do you come up with such a large number?
Well, we have the formulas for the proton atomic mass units already.
Very good,
And
you're
we
on the
knew
right
that
track.
They were really small.
Very good. You're absolutely on the right track there. So once you know the mass of the number of protons and neutrons, remember that's where the mass is coming from. So once you know the mass of the protons and neutrons, all you have to do is inverse it to get this, the number of atoms. Okay, in there, and that's what Avogadro did. It may be a little bit more complex than that because he has to account for some other things, but essentially that's what he did. Okay, so you take the mass of that kilograms that we were talking about, 10 to the negative 27, was it? So 10 to the negative 27, and you inverse that, and that's how you get this big number, okay, in there. So, in general, 1 mole of people is equal to how many people?
6.023.
Times 10 to the 23.
Yes, that many people. Not on Earth right now. Not that many yet. Okay, but that's 1 mole of people. Well, I'm just trying to tell you the concept of mole. Okay, that's what mole stands for. So if you say that you have the 1 dozen people here, 1 dozen people means you have 12 people here. Okay, that's what it stands for. So when you say you have 1 mole of people, that means you have this many people. 1 mole of M&Ms, that would be heaven. Yes, that would be good. Okay, so too many M&Ms there. Okay, but that's what mole stands for. Okay, it's like a dozen thing. It's a measurement. Okay, that we use. So then when you have mole, how do you relate that atoms to the mass? And that has to do with the periodic table then. That's the mass number that you use. Okay, so it doesn't make it very difficult later on then. So 1 mole of chromium has this much mass. 1 mole of molybdenum will have this mass. And obviously 1 mole of atoms of molybdenum will have higher mass than chromium because it has more neutrons and protons. Okay, and that's why it is heavier. So the same number of atoms will give you more mass for molybdenum and then even more mass for tungsten because now you have even more protons and neutrons. Okay, all right. So that is the mole concept, okay, in there. So now let's look at something else. Let's come back to our beautiful water. We'll break it down a little bit. And water is H2O, which means you have 2 hydrogens and 1 oxygen. Now I want you to start looking at it a little bit different because until now you were looking at it as a ratio of 2:1. That you have 2 hydrogens and 1 oxygen. Now I can think of it different ways. You can say you have 2 moles of hydrogen and 1 mole of oxygen. Okay? Now you start thinking in terms of mole ratios over here instead of just atomic ratios. Okay? So if you have magnesium nitrate, where you have 1 magnesium, 2 nitrogens, and 6 oxygens. Now you have 1 mole of magnesium, 2 moles of nitrogens, and 6 moles of oxygen. Okay, so that's your mole concept right there.
And if we wanted to add up how many atoms in there, you would multiply all of those.
All of those by the 6.02 times.
And then you add them together.
You would add them together, exactly. So if I were to ask you the total number of atoms here, then yes, times 6.02 10 to the power 23, and this is 1, and this would be the same, but you'll be multiplying it by these numbers. Okay, yeah, and once you have the answer, add it. Okay, all right. Calculation to do. Okay, because we had 12 grams over here of carbon, and I asked you to calculate for 6 grams, it was just half. Okay, but of course I'm never so kind. Okay, because it's not going to be 6 grams, it's going to be say 1.23 grams. Now tell me how many atoms I have. Okay, in there. So which means that you need to be able to do those manipulations. For those manipulations, you're going to use all of these as your conversion factors. Okay, and you can use these as a conversion factor for anything. Okay, you can convert atoms to moles, moles to atom, moles to grams, grams to moles, however you want to. So for example, for carbon, it is 12.01 grams per mole. You can inverse that and you can say I have 1 mole over 12.10 grams also. It's the conversion factor. So if I'm asking you to calculate some gram value into mole, this is what you would use. If I ask you to convert some mole value into gram, this is the conversion factor you will use. Okay, so that's your conversion. For atoms, same thing. Okay, so in 1 mole, you have 6.02, and usually we don't even use 3, 10 to the power 23 atoms. Okay, or you can use it the other way. Yeah, 1 mole. To go from number of atoms to grams, I usually go through moles for everything. Moles is my center point. Just like in chapter 1, I told you I always go to the base. Okay, always go to my base unit and then I go anywhere. When I do my mole calculations, I always go to the mole. So if I have to convert number of atoms to grams, I will convert the atoms to moles first, and then from moles I will go to grams. Okay, from there. So that's what I will do there. Okay. Good. One little thing I want to check, because there was one thing that I wanted to give you over here for your weekend work. Okay, is calculating mass percents. And mass percent, there are some here that you can do and some you will not be able to do. Okay, but sodium chloride, NaCl. If I asked you to calculate the mass percent of sodium in sodium chloride, it's not going to be 50%, even though the ratio is 1:1, okay? But the mass percent is not going to be 50-50 because the masses of sodium and chlorine are not the same. Okay, so the mass percent is not going to be the same for that. So in that case, what you will have to do is take the masses, okay, from the periodic table. So here NaCl becomes 22.98 and Cl is 35.45. That's the total mass. And then since you're calculating for sodium, percent sodium is 22.98 divided by the total of that. Let's do that real quick here. It's about 58 something, I think 58.43. 58.3? 43. Okay. And you can use AMU for mass percents. It's all right. You can use grams per mole if you want for mass percents, because eventually it's going to be a mass percent. Okay, so your units will get crossed out, so it doesn't really matter. And then times 100%. And if you were to do percent of chlorine in there, then it would be 35.45 divided by 58.43. Again, AMU times 100%. And let's do those calculations real quick. I know Summer is already working ahead of me. Yes, 22. I have to work faster than her.
If I have it up, I'm not gonna make you do the calculation.
Okay, here we go, 39%, and I'm just rounding it off a little bit. And 35.45 divided by 58.43. It's a redundant calculation because I can just subtract from 100%. Okay, but still. Okay, here we go. So this is about 61%, which is fantastic because if I should add them, they should come up to be 100%, right? Okay, which means that the mass that is contributed in NaCl by percent, even though this is a 1:1 ratio, but the mass percent contributed by chlorine is a lot more, obviously because it's heavy, okay? So the mass percent contributed is a lot more, okay, than by sodium. And these kind of things become really important when you're thinking about your sodium intake, your calcium intake, you know, how many atoms you're consuming. So this becomes really important in that. So this is mass percents. If you were to do it for multiple atoms, let's do that one thing. I will take my trusted calcium sulfate. So if you were calculating the mass percent of sulfur over here, it would be the mass of sulfur divided by calcium sulfate. So you'll add calcium, sulfur, and 4 oxygen in there, right? All of that times 100%. That will give you the mass percent contributed by sulfur, okay? So you can calculate the mass percent contributed by each substance in this.
So it was something like 2 chlorine, or chlorine 2. It would just be 50%, wouldn't it?
That would be 50%. So if you have a diatomic atom, yeah, then it's 50%. You don't even have to do any calculations there. But as soon as you have something that is different, then you have to calculate this out, okay? So that's, yes, Jake?
Wouldn't it be 100% if it was diatomic, and calculating percent of it?
Yeah, so it's half over the 2. It's 50%. Yeah, Cl2, for example, it's the bottom mass is going to be twice that of Cl, right?
But if you have 2 chlorines,
If you have 2 chlorines, if you're doing Cl2, this is going to be Cl over Cl2, so that's half of it. Yeah. Okay.
But if you're trying to find out the mass of, oh,
The mass percent also will be 50%. Yeah, because it's the same atom, okay, in there. All right, very good. So